Now we're going to talk a little bit about humidity because this is when things get a little bit more interesting when we talk about how weather and water play a role in our atmosphere. So when we talk about humidity, we're really talking about how much moisture is in the air. So when we talk about moisture, we're really talking about the water vapor. So how much water vapor is in the air. Now we introduce a second term called absolute humidity. And absolute humidity is simply just if you were to extract all the water out of the atmosphere and you were to measure that amount, how much water would you actually have? And so think of a dehumidifier. And if you've ever had a dehumidifier in your basement, what does a dehumidifier actually do? It takes the moisture that is in the air in a basement and it pulls it so we don't occur mold issues. And so if a dehumidifier runs for, let's say, 24 hours, at the end of its 24-hour cycle, you have to empty the bucket in the dehumidifier. So when you empty out a bucket, it's normally full or it's chock full with water that was once suspended as water vapor in the atmosphere of the basement. So when you pull out that bucket that's filled with water, you can actually measure the amount of water. You can weigh it. You can see how many inches of water that is in the bucket. So that would be an example of absolute humidity because you are extracting water out of the atmosphere and you are actually measuring it. So how much water vapor is actually in the air. Now, it may seem a little bit more difficult to actually physically extract all of the water out of our atmosphere, and we wouldn't want to do it anyways. So therefore, how do we measure things like relative humidity or atmospheric moisture in the first place? Well, we first need to understand what a mixing ratio is. And a mixing ratio is really just the amount of water in a unit of air compared to the amount of dry air within that air parcel. So it's really just a ratio. So think about you took a quiz in a certain class and the quiz was worth 50 points and you received 40 points out of that 50 points. Well, we know you didn't get a perfect 100 because you would have gotten 50 points out of 50 points. But let's say you got 40 points out of 50 points, or roughly 80%. So that is how relative humidity is calculated based off of knowing what the mixing ratio is. So if you take this image, which is just any typical air parcel, and in this air parcel we have parts of nitrogen, we also have some water vapor, we have oxygen molecules, we have some other constituents in this air parcel. All the mixing ratio says is how many water molecules that look like Mickey Mouse ears are there compared to all of the other molecules within this air parcel. And that's what the mixing ratio essentially is. Now this is important because this plays a huge role on atmospheric pressure. So we know what pressure is. It's just how many molecules are in a certain parcel of air, especially when we talk about air pressure. Now your book talks a little bit more about vapor pressure or water vapor pressure, and that's basically the amount or the partial pressure that is solely due to water vapor content. So if we go back to our visual example, vapor pressure just says how much of the total atmospheric pressure that is due to the amount of molecules that are within this solo unit of air. And you have to understand that our atmosphere comprises of a bunch of these tiny little air parcels, all that have certain amounts of things like nitrogen, oxygen, water vapor, carbon dioxide, argon, some of the trace noble gases, so on and so forth. Vapor pressure just says how much water vapor contributes to the total amount of pressure within this air parcel. Now we can take that a step further and talk about the saturated vapor pressure, which is just the vapor pressure when the air is saturated. Whereas when we talk about saturation, it is the number of molecules evaporating equals the number of molecules that are condensating. So when we say that an air parcel is saturated, that means that it cannot hold any more water. Meaning to say that air parcel is full it can't hold any more. You can't get rid of the oxygen in that air parcel. You can't get rid of the nitrogen in that air parcel, but you can get rid of the water vapor in that air parcel. And this is really the very, very baseline idea on how precipitation works. So when we say an air parcel is saturated, that means that no more water can be held in that parcel of air. So in this example, we have two beakers. One beaker is just comprised of a little bit of water at the bottom, but most of it is dry air and has an internal temperature of 20 degrees Celsius. The other beaker also has an internal temperature of 20 degrees Celsius. It also has a little bit of water in its bottom portion, but that water is actually evaporating. So what you notice between the pressure gauge on A and the pressure gauge on B is that the pressure gauge on B is now increasing. So the total pressure within this beaker is increasing. And that makes absolute total sense because you are actually adding, if you're evaporating this water, you are adding water molecules or you're adding vapor pressure to the constituents that are already in this beaker. So therefore, you're adding more people to a room, therefore the room is going to become more crowded. So if you can understand that concept, you can apply it to air and water vapor. If we take it a step further, you look at the beaker part C and you look at the other beaker at part D, well, we're basically just doing the same thing where we're evaporating water as the pressure gauge goes up, but now we're evaporating water and adding heat. Now, what does the ideal gas law say? If we're increasing temperature, we have to be increasing what? We have to be increasing pressure. So not only did we go from a dry beaker to adding water vapor to that beaker, we saw that the temperature went up. So now what we do is now we're adding heat to that equation and we're watching the temperature go up. So imagine a small or relatively small conference room at some place of employment, and that conference room was chock-packed with people. Let's say the room could comfortably hold 20 people, but 40 people were in this conference room. Well, everybody is shoulder to shoulder, and that might make people feel a little bit uncomfortable. So if somebody's feeling uncomfortable, what might happen to their body? Meaning to say their blood pressure might go up. Now let's take it a step further and say, now we have 40 people in a conference room that could only comfortably hold 20, and then we kicked the heat on and we made that room 100 degrees. So now everybody is right on top of one another. Not only that, but we're adding heat to the room, so now people are twice as uncomfortable. So what might happen? That might be a really heated conference. People might get aggravated. People might have their blood pressure increase or watch people's blood boil, if you've ever heard of that phase. So if you can imagine that kind of scenario, it's the same idea with water. When you add heat, you're increasing temperature, therefore you're increasing pressure. And if you add water vapor, you are also adding to the total atmospheric pressure.